Ron Richards is a lucky man. He was right near a level 1 trauma centre when the car hit him. After sustaining multiple leg fractures, a smashed pelvis and a crushed chest, Ron's heart stopped beating in the emergency department, but the medical team brought him back to life. In theatre, he receives massive blood transfusion and life-saving surgery.
The good thing that everything went very well, so we managed to control his bleeding from the chest and the pelvis.
But days later, while recovering in intensive care, Ron's organs begin to fail, one by one. First, his liver starts to deteriorate. Then his lungs fail, followed by his kidneys, dramatically lowering Ron's chances of survival. It's an all too familiar story in trauma units across the world. A patient survives the initial injuries and then dies from multiple organ failure.
Everyone happy to go the rest of the way on 3?
Yeah,
1, 2.
Why it can happen to severely injured patients like Ron has so far been a mystery. Now an Australian team is beginning to unravel the cause, and it offers a strange glimpse into the ancient life within us all. Ron was walking along this grassy verge when he was hit from behind at 60 kilometres an hour. That's a force greater than the human body is evolved to withstand.
The highest energy injury 100 years ago was falling off from a horse. Fracture here on the pubic rami.
These days, we not only travel at great speeds, but medicine is also moving forward at a cracking pace. It means patients like Ron can now survive the unsurvivable.
We are faster getting the patient into hospital, or resuscitation strategies improved. We use more blood and blood components, or surgical techniques may be faster. During the last 30 years, trauma care improved tremendously.
Ironically, this has led to the emergence of a deadly secondary condition, multiple organ failure. The strange thing about multiple organ failure is it usually sets in 3 to 5 days after severe trauma, without any sign of infection and without any injury to the organs involved.
So by that stage, they're looking pretty swollen and not like themselves at all. Their blood pressure will start to go down and their heart rate will go up. We also see it in the way their blood tests start to deteriorate.
As the body becomes more inflamed, lungs, liver, heart and kidneys begin to shut down.
Everything's going wrong at the same time, really. It's very serious, and that, unfortunately, they're much more likely to die.
It's the #1 killer of trauma patients who survive serious injury. Doctors have been trying for decades to figure out what triggers multiple organ failure. But it wasn't until a few years ago that a team in Boston came up with the vital clue. In the blood of severely injured patients, they found high levels of free-floating DNA. But it wasn't DNA from the human chromosome. This DNA belonged to something that can trace its origins to a much older time, around 1.5 billion years older. What they found was very high levels of mitochondrial DNA. Mitochondria are the powerhouses of eukaryotic cells, which make up some of the most diverse creatures on Earth today, from plant life to fish to mammals.
One of the benefits of having mitochondria is that you can produce energy cheaply. And so if a cell has high energy demands, you need a lot of mitochondria.
What's peculiar about mitochondria is they still retain their own primitive DNA.
Mitochondria have their own genome. It's much smaller than the nuclear genome, and it's circular. And that's very similar to what you find in bacteria.
It's thought that 1.5 billion years ago, a bacterium was engulfed by a single-celled organism, creating the eukaryotic cell. But the ancient DNA stays safely locked away behind a double membrane and never enters our bloodstream. At least, that's how it's supposed to work.
The tissue injury due to trauma causing cell disruption, cell death, and all the contents of the cells leaks out.
Cell death on a massive scale explains the high levels of mitochondrial DNA found free-floating in the blood immediately after severe trauma. But it didn't explain why multiple organ failure sets in 5 days later.
To me, it was still a mystery.
The team in Newcastle decided to take the experiment a step further.
We monitored patients up to 10-15 days after injury.
To their surprise, after an initial decrease, levels of mitochondrial DNA in the blood began to suddenly and rapidly increase, without any further injury to the body.
So this increase here doesn't make any sense to me. We first thought that this is something wrong or error in our measurement. DNA.
Oh no, it's huge.
Levels peaked exactly when multiple organ failure usually sets in.
In day 3, day 5, it was very, very high, higher than at the time of the injury.
The markers of
The only way mitochondrial DNA could increase in this way was if it was somehow escaping from living cells. But how this would be happening in trauma patients was an unknown. Professor Barlog went back to the latest research to look for clues.
So he found in infectious disease literature, white blood cells, when they encounter bacteria, they do an extraordinary thing.
When confronted with bacteria, white blood cells, or neutrophil leukocytes, behave like predatory spiders. They spit out a web or net to trap the invaders, then hit them with a deadly oxidative blast.
Mitochondrial DNA is very similar looking like a bacterial DNA. And if bacteria is triggering leukocytes, we thought that maybe the mitochondrial DNA does the same.
What's more, the nets themselves had been shown to be full of DNA. If this happened to be mitochondrial DNA, this would trigger even more white blood cells to attack, causing a vicious cycle of inflammation. To test the theory, the team from Newcastle separated the white blood cells of severely injured patients and used coloured stains to identify the DNA. Under the microscope, this is what they found. The blue stain shows up living white blood cells. The green stain shows up any DNA escaping from those cells. And it was clear these cells were in attack mode, literally bursting their DNA across the screen. So is that green burst a net in action?
All these green stained areas are nets.
A further red stain shows how much of the DNA in the nets themselves is mitochondrial.
And for surprise, this is
All
what
of
we
it?
saw.
It
Yeah,
must have been amazing to see.
it was an amazing discovery to see.
The stains confirmed that mitochondrial DNA is the culprit behind the deadly inflammatory cascade in multiple organ failure.
It's very fascinating that the inflammation after trauma is driven by our own body.
The attacking white blood cells migrate from the bloodstream into major organs. Here, as they spit out more nets and continue their toxic oxidative blasts, they cause mass tissue damage, leading to total organ shutdown.
I'm studying multiple organ failure in the last 20 years. Nobody knew that cells can do this in trauma without infection. Just amazing.
Yeah.
This is what we thought gonna happen.
yeah.
It's a fascinating example of just how far we've come down the evolutionary path. Some parts of our cells originate so far back in time that they appear alien to our most vital processes. These nets are moving into the spotlight in many other areas of medical research, including heart disease, stroke, and cancer. Monitoring mitochondrial DNA levels in patients like Ron can help time surgery better to avoid the extreme inflammation that leads to multiple organ failure. Doctors can also rapidly distinguish between infection and trauma-driven inflammation. As for Ron, his organ function returned to normal, and he's begun the long road to rehabilitation.
How are you feeling? All right? Doing that all right?
Yeah, I just feel so happy to be here and talking to you. Very nearly wasn't.
Okay, very well done.
He still considers himself a lucky man.
That's great.
Next time on Catalyst, are we eating ourselves sick? In the first of a two-part special, I take a look at remarkable new discoveries about food and the trillions of microbes living in our gut. Connect with Catalyst on Facebook, Twitter, Instagram, YouTube and our website.